Okay, I think we'll go ahead and get started with our next Ivan Roundtable workshop for NMR research, Molecular Conformation via NMR. At this time, I will pass it over to David Rice.
Okay, thank you, Eric, and I'll also welcome everyone. It looks like we're going to have another very well-attended meeting today, and I think a very broad and general and good topic. So let me hand things over to John.
Thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. And let's not forget happy summer solstice, winter to the folks in the south of us, of course. And I think this is Ivan meeting number 36. And since we've been doing our little Zoom online experiment for well over a couple of years now, once again, great subject material today. I've got very, very good panel lined up and looking forward to it. MR Resources and Q1 Instruments are very happy to be bringing the Ivan meetings to you. And MR Resources, of course, have been around for over 35 years at this point, and providing reconditioned NMR systems, magnets, consoles, probes, service contracts, quench magnet recovery, and certainly moving and relocation. In fact, they've got a very impressive inventory of reconditioned instruments on hand, and 3 in particular, very spectacular offering, all Brooker Avance 3, 600, 700s, and they've even got a 950 in inventory at this point, all with cryo probes. Certainly check them out, get in touch if any of these interest you. And Q1 Instruments, a little bit newer to the industry, but Eric, could you give us some brief information on Q1, please?
We invite you to get to know Q1. Q1 designs and manufactures NMR spectrometers from 400 to 600 megahertz with features for routine use and the research laboratory. Want to upgrade an older system without blowing your budget? Q1 can retrofit AS and UltraShield magnets with complete upgrades, including automation, for less than you think. Q1 offers NMR instruments with excellent performance at an unbeatable price. Experts know the key to performance is the probe, and Q1 offers smart tune and match probes made by Q1 Tech. Q1 Tech has decades of experience and leads the market in innovation. Q1 STM probes have a patented hybrid tuning mechanism, which means faster tuning, improved throughput, and unmatched reliability. Q1 offers their 400 megahertz instrument with STM probes in 3 configurations. A 2-channel probe with fluorine tuning on both X and H channels for maximum flexibility. Or fluorine detection can be isolated to the X or H channel to maximize H sensitivity or to maximize carbon and phosphorus sensitivity. Q1 Tech STM probes are also integrated into Topspin and VNMRJ for improved performance and throughput for existing installations. To know more, our websites have additional info. We're also happy to provide remote demonstrations with your samples. Please contact us by phone or email.
Thank you, Eric. Very capable lineup. Please do check out Q1 Instruments. Krish, could you give us some information on upcoming meetings, if you would, please?
Thank you, John. Welcome, everyone. As John pointed out, we are in summer, but our lineup is pretty much getting filled until the end of the year. I wanted to give you some introduction on that. Next month, that's in July, we will have a workshop on polymer NMR. It will be led by Jackie Thomas from Procter & Gamble. She will be joined by Ben Reiner in Dow and Lou Matson from Virginia Tech. Following that, we have 4 workshops coming, one after the other. One would be an Ivan user conference follow-up, because we had some technical issues during the conference at ENC. A few of our speakers got left behind, and so we are going to do a follow-up on that, followed by an application of benchtop NMR in industrial settings, NOVA sequences, and also introductory bio-NMR as well. So that will still pretty much we are coming to end of the 2022. This is very good because of your support, and I appreciate that. With that, I will turn that back to John for this meeting. Thanks.
Krish, thank you very much. And wow, we're just going to keep these things going for, quite some time to come, as far as I'm concerned. And very good future meetings, as you say, lined up pretty much through the end of this year. Anyways, without further ado, over to Dave. And Dave, if you would like to kick things into high gear for us today, please.
Okay, why don't I just go right ahead and do that? Let me hand things over to Misha.
Thank you very much. I thank you to Ivan, organizers, for giving us an opportunity to talk about this fascinating topic today, molecular conformation via NMR. I'll give very brief introduction before late panelists present their work. So molecular conformation, as many people already know, that this is a really, really broad topic, and there is no way we can cover it in an hour here. I just wanted to give a slight background to the slice of molecular conformation that we'll be talking about today. Of course, NMR is a fantastic information-rich technique that can do a lot of things. I don't think I need to convince anybody here. Among many other things, NMR is great for determining molecular conformation. There are multiple NMR measurables that are directly contributing to or influenced by conformation. In some of them can be interpreted really directly. NOEs, ROEs, of course, correspond to interatomic distances. Coupling constants correspond to torsion angles through Karplus curves. Other measurements are less direct in interpretation, but no less important. So chemical shifts, and recently anisotropic NMR has really become very popular, and those also depend on conformation. So one way to interpret them is to calculate them for all conformers and then compare with experimental measurements. On this workshop, we'll be focusing on this angle of molecular conformation. It is more of a biochemistry pharmacology application. So why is it important? Again, there are probably 24 good reasons why we want to study molecular conformation via NMR. Today, we'll be focusing on pharmacological applications, and the most important is the top line is free solution conformation of a ligand versus bioactive conformation when it's bound to a target protein. So these two conformations are not necessarily the same, and this has absolutely profound implications in both in studying mechanism of action of natural ligands and in drug discovery, design, and development. Typically, structural biology focuses on the bound conformation, but solution conformation is no less important because it could be quite different. Also, I would make a strong statement, solution conformation is very important to determine experimentally because it may or may not correspond to computed energies of your conformers that you generate in silico. And having some sort of experimental validation, or for complex molecules like macrocycles, direct experimental restraints is very important in order to make sure that conformation, free solution conformation is congruent with experimental data. I'll give a little teaser here and a shout out to the 4th gen software developed by AJ Jain and Ann Cleaves. This is a software where I did a collaboration, and this little map shows you that the conformational space with very few NMR constraints could be quite a bit different from the conformational space for an agnostic search without any constraints. And that is, for complex macrocycles, that is pretty typical. Another significant implication is so-called strain energy. That's the energy difference between energy of the free conformation in solution versus energy of the same ligand when it's bound to its target. And it could be very, very significant because, of course, interaction with the protein provide an additional enthalpy to counteract it, to compensate for it. So once again, the solution conformation could be entirely different from the bioactive one. And it's very important to study it experimentally by NMR. And I would be remiss not to mention permeability. I think cyclodextrins cyclosporids remain a gold standard for how molecular conformation impacts permeability. This is a standard paradigm by now that in one conformation, cyclosporin binds its target protein, and the other conformation in the lipophilic phase, it transits through the membrane. So that's enough for the for my introductions. Before we start with the presentation, just a couple of programming notes. Please feel free during the presentation. Please feel free to type in all your questions in the chat. We'll try to answer them after the presentation. But if usually we only have time for a couple, and most of them will be answered in the follow-up conversation. And during general chat, please just unmute yourself and ask questions. This is intended to be as a open discussion for all. And let me introduce the first speaker. Let me stop sharing. Let Donovan bring up his presentation. So the first speaker will be Donovan. Dr. Donovon Adpressa received his PhD in chemistry from Oregon State University under the mentorship of Professor Sandra Losgen, working on discovery and structural elucidation of novel fungal natural products. After graduating, he moved to work at Merck & Company as a part of structural elucidation group and later analytical enabling technologies. During his tenure at Merck, Donovan supported discovery and development efforts, performing structure elucidation, structure characterization, free ligand conformation analysis, absolute configuration determination, and development of innovative methodologies to address challenges across the pipeline. Recently, Donovan returned to his home state of Colorado to join Loxo Oncology at Lilly team as a principal scientist in analytical chemistry, focusing on structural elucidation, reaction characterization, and capability development in support of discovery chemistry and CMC. Donovan, please take it away.
Thank you very much, Misha. Thank you for inviting me to be a part of the panel today. Thank you for the organizers for putting this together and the other amazing panelists and to everybody online today. So today I'll talk about analysis of the solution conformation of a stapled peptide. That discussion will focus around a homologue of ASTP 7041, which you see on the right here. We've just changed one residue. ASTP 7041 is known by ECD to form a helical structure and by X-ray crystallography to form a helical structure. However, until our analysis, no solution NMR structure was undertaken. And during our analysis, we developed a workflow to make things a little more high throughput. NMR analysis can be pretty slow, especially when we first need to optimize our aqueous conditions to figure out what will work. And so we prefaced our NMR and computational analysis with size exclusion chromatography, hydrogen deuterium exchange mass spectrometry, and circular dichroism before moving on to NMR constraints and computation. And the reason we do this is because if we compare our peptide, which is the green solid line, and I've highlighted our chosen conditions in beige. If we compare it under a number of co-solvent mixtures or a number of temperatures, we can figure out exactly where we'll have a stable conformation. So up top on the left-hand side, we can see that at almost any percentage of acetonitrile, we retain about the same amount of deuteriums. And at the bottom, we can see that if we change temperature up to around 35 to 40 degrees Celsius, we retain the same amount of deuteriums. And so that gives us a really good guidance on where we can take our NMR experiments without losing the fidelity of our solution structure. ECD adds to this, and we see a very similar trend in the top right plot, again highlighted in beige. We see that the amount of acetonitrile co-solvent has little to no effect on the helicity of our peptide. However, we do know that between room temperature and 40 degrees C, we continue to lose helicity. However, sometimes we have to make some sacrifices. And to get the most quality spectra, we did choose 1-to-1 acetonitrile at 40 degrees Celsius for analysis. And I think the reason why becomes quite apparent when we look at our spectra. So the top spectra is the very same peptide as shown in the bottom spectra, just in fully aqueous conditions, also at 40 degrees Celsius. And it's essentially unanalyzable. We don't get high enough solubility to even see the peptide signals unless we, really dig into the noise. However, if we increase our signals to 1-to-1 acetonitrile water, we get beautiful spectra. And if we heat it up just a little bit outside of room temperature, we get nice sharp lines that allow us to measure J couplings that are important for our analysis. So that's exactly what we need to determine our conformation. We need to take our experiment observables such as distance and torsion values like that Misha mentioned. We can pull those from our ROSI or our NOSI or selective experiments. And for our torsions, we can take those directly from our proton spectra, or even go more exotic and look at het core IPAP spectra to determine JXH torsion angles. In this instance, we just relied on ROSI and proton spectra. And from that, we were able to select a set of very sparse restraints from just the backbone atoms. 12 distance restraints taken from the ROSI that you see on the screen, which thanks again to our pre-screening is very high quality, nice sharp signals, easy to discriminate signals. And then 8 torsion restraints from our NHHA coupling constants. And from there, we feed these into ForceGen, which Misha already gave a shout out to. And so we'll take those and we will build a table of our upper limits and for torsions, a range. I think it's really important to take a moment and stop and appreciate how easy ForceGen makes this. The table that I have in front of you is essentially what you feed into ForceGen, just as a text file with the headers removed. And there are a lot of other important features included, such as this ability to have a range. We know when we have a small coupling constant, that doesn't always mean that it's at 60 degrees. It could be at 45.9 degrees. And so we want to give some range to our restraints, be it torsions. And then we also have this set energy penalty. So for instance, with our NOSIs, just because we hit an upper limit of 3.4 angstroms doesn't mean a conformer will get kicked out of the ensemble. If it's low enough energy that the restraint violation energy is accounted for by the force field energy, we'll go ahead and keep that restraint and see it in our final input. And we'll get an ensemble that hopefully looks something like this, which is our return to peptide 1. These are the lowest energy 100 lowest energy conformers when we consider both force field energy and restraint violation energy. And so we can see that we get a very nice agreement. We get a helical peptide as we expected. Most of the conformers are in agreement except for that last floppy residue we've added onto ATSP 7041. And in fact, the agreement's so great that if we do a pairwise analysis, we find that the mean pairwise RMSD for the backbone heavy atoms is just about an angstrom. And for all heavy atoms, we're looking at about less than 2 angstroms there. Finally, we want to make sure that our solution conformation is actually the solution conformation. We don't want to just rely on what we've thrown into our computational tools. And so we can actually step backwards and see if the ensemble we've arrived at matches the experimental data we've seen. And so the first experiment we ran was hydrogen deuterium exchange mass spec. And we see that at 1:1 acetonitrile and 40 degrees Celsius, we retain approximately 8 deuteriums. We also ran some 15 NHSQC observed variable temperature experiments to determine which amides might be involved in backbone hydrogen bonding. And we find 8 backbone amides are involved in hydrogen bonding. And if we look at our model, we find that across the 100 best structures, we have an 8.9 average hydrogen bond. So we find that we have a really good agreement between our computational conformational analysis and experiment. And with that, I will thank everyone once again for their attention and open the floor up for questions.
Thank you very much, Donovon. And we actually have some time for questions. So feel free to unmute yourself and ask questions. And I can start. Donovan, I think this is a very nicely presented work. I think probably good idea to provide the context of how experimental NMR data are used, because you can use experimental NMR data as explicit restraints, or you can use it as implicit validation tool. So can you comment on that? What do you think is better, and how do you think, how would you go about this?
I'm sorry, can you say the very last sentence? You can use it as implicit.
So some NMR data, the most obvious use of NMR data is explicit constraints, are distance constraints and torsion constraints. And other types of NMR data can be used as a validation of your final structure. So which is, you demonstrated really nicely with the HDX data. What else do you think could be used for the for such approach?
What else do I think that could be used? Well, we certainly only used, you know, some just really one implicit restraint, and that is making sure that we had an agreement again between backbone hydrogen bonding. We could certainly turn to RDCs or RCSAs to see if we have another implicit agreement there between our conformational ensemble. We could also use even more restraints from the get-go. Here we only used a total of 20 or so, 21, I believe, restraints. But we could go back and we could again look at additional implicit restraints that we might not be as confident in. For instance, if we take a look back at a ROSI, there are several areas that are just too crowded to feel really confident at first pass. And so we can return back to our model and say, well, we think we see a ROSI here. Is that really a cross-ring ROSI that we see? And, you know, is that explicit or implicit at that point? It starts to blur the line since we have less confidence in it. But yeah, does that answer your question, Misha?
Oh yes, very much so. Thank you. Yeah.
Fantastic.
Yeah, well, yeah, of course, you can go. It's very natural to go from implicit validation into refinement, and the line is indeed blurred.
Is it fair for you to ask questions since you're an author on the paper? Oh.
So actually, I have a question. If you, yeah, it was a nice presentation. This is Prashansa. So I saw the final structure. So the last part of it is quite flexible, right? Is there any specific reason why it is happening?
Yes, that residue I can't entirely disclose, but it's essentially just a lysine hanging off on the end there, and so it has no higher order structure to retain it, and so you're essentially just looking at a lysine flopping around through space, which we completely expected.
Got it. Okay, thank you.
Hey, Donovan, a quick question. This is Gennady, by the way. You mentioned you ran N15 observed HSQCs. Were you just looking at temperature coefficients, amide temperature coefficients to get a sense of the hydrogen bonding?
Exactly. We were looking for temperature coefficients greater than -4 parts per billion. You can see the tight clusters on the screen. I'm not sure if you can see my mouse, but you can certainly see, which clusters corresponded to hydrogen bonds in our backbone.
Thank you.
We have a question from the chat. Please, Sean, please feel free to voice your own question.
Was the HSQC done at natural abundance, or was that done with labeled peptide?
It was done at natural abundance.
And how much peptide did you need to use for that?
We were at 20 millimolar for all of our studies.
Okay, thank you.
Should know on a Prodigy cryoprobe too. Maybe that's a.
I have a question on that subject. It's ET, Evgeny Tishenko from Joel, USA. Since we mentioned hydrogen bonds and 15 NHSQC, it looks like your peptide is relatively small, concentration is relatively high, and probes are relatively sensitive. So there is a chance to try an experiment that gets through hydrogen bond J couplings, nitrogen, carbon, proton, carbon, proton, nitrogen.
I certainly tried very hard using SOFAST HMBC to see if I could get through hydrogen bond couplings. I don't think it's possible for this molecule without labeling.
Okay, fair enough.
Thank you very much, Donovan. I think we can move to the next presenter today. And our next presenter is Dr. Amber Balazs. Dr. Amber Balazs received her PhD in 1999 in biological chemistry, investigating transmembrane signaling using solid-state NMR under the guidance of Professor Lynn Marie Thompson at the University of Massachusetts in Amherst. Then she did a 2-year postdoc at the Weizmann Institute of Science in Israel in the group of Professor Shimon Vega. Then moving north to Technion, Israel Institute of Technology, she worked as an NMR facility manager in the Shulich Faculty of Chemistry, helping graduate students and postdoc with solution NMR investigations. In 2016, Amber joined AstraZeneca's early oncology Boston research and development site in Waltham, Massachusetts, working on small molecule drug discovery as an NMR specialist and team lead within analytical and structural chemistry. Amber, please go ahead.
Thank you, Misha, and the Ivan Organizing Committee for this opportunity to talk about our NMR free ligand conformational platform at AstraZeneca. What is on the agenda? First, a brief introduction to our working hypothesis that potent synthetic drugs free in solution favor pre-organization into the bioactive conformation. This is a guiding principle. Under 1D NMR conformational signatures and dynamics, I'll highlight 2 published macrocyclic examples, plus 1 acyclic example published last year, incorporating molecular dynamics. Thirdly, 3 unpublished NMR conformational analyses with a highlight each on potency, permeability, and populations across solvents. Then a summary and key learning slide before opening to Q&A. As potent synthetic drugs free in solution favor pre-organization into the bioactive conformation, let's use medicinal chemistry design to lock in the bioactive conformation of the free ligand in solution to optimize potency. In this 2019 Future MedChem commentary by 3 of our leaders, movers, and shakers, underutilization of experimental NMR free ligand conformations is addressed. Structure-based drug design to improve ligand potency is well established, and it can be enhanced by including an analysis of the bound versus free ligand solution conformations. Another 2019 publication from our team looked at free ligand 1D NMR conformational signatures. We were identifying conformation reporter atoms where the NMR chemical shift is sensitive to and diagnostic of the 3D solution conformations. In this example of AZD5991, the 5.8 ppm value comes from an ACD Labs 2D structure-based empirical chemical shift prediction for the circled pyrazole CH, which is usefully flagged with a red color as a prediction that is a potential conformation reporter atom. In order to calculate ring current and other effects arising from 3D molecular conformations, QM calculations are needed. The bioactive conformation QM chemical shift calculation of 4.8 ppm matches the experimental NMR spectrum of the free ligand in solution. In contrast, the non-bioactive conformation, its 3D QM chemical shift calculation of 4.1 ppm is a poor fit. So one key challenge in our drug discovery setting is the importance of speed for the information we find to be practical. And one thing we NMR spectroscopists can do is to work with the project teams to help identify 1D NMR conformational signatures. And this information about free ligand populations under experimental thermodynamic equilibrium can help guide and test design ideas within a drug project. From the same paper, we described a linker optimization. This is a methyl scan, and how this CH reporter signal in the 1D NMR spectrum correlated with potency to deconvolute free ligand preorganization, those contributions influencing the binding on rate from protein ligand interactions, and that complementarity influencing the ligand residence time of the bound ligand. This check mark here means that the free ligand bioactive conformation is highly populated in solution, and that's based on the proton NMR chemical shift. The protein binding potency is given on the right, and bioactive preorganization of the free ligand, but low or medium potency is rationalized by poor protein ligand interactions or complementarity. So this structure activity relationship, or SAR by 1D NMR, and thanks to Neil Zondlo for the catchy title, can help guide drug design and test design hypotheses. From the publications, you can get experimental details and more examples. This third paper focused on NMR free ligand conformations and atomic resolution dynamics. On the proton NMR spectrum, the blue highlights the benzylic CH singlet, and integration of the rotamers shows equal populations of the two conformers that are undergoing slow exchange on the NMR timescale. On the far right, in blue, is the calculated torsional energy barrier to rotation for this bond of 20 kcal per mole, which agreed with the NMR determined value. So these molecular dynamics calculations are providing prospective evaluation of rotatable bonds to focus design efforts and rank compounds for MAKE, and can help simplify interpretation in NMR analyses. So next up are highlights of unpublished NMR conformational analyses. We've got a potency example with AZD5305, So I'll just show some practical tools, then an example with permeability using free ligand NMR solution conformations for drug property relationships, then an AZD9833 example of free ligand solution populations across solvents. AZD5305 is a PARP1 DNA trapper with high selectivity. This reference tells of its discovery, while shown here is the solution conformation and that it's bioactive. In this top left panel, the 3D bioactive conformation of the bound ligand is shown in green. Superimposed in gray is the free ligand experimental NMR analysis of molecular flexibility in solution. For this potent and selective binder, these agree. The bottom left highlight is the atomic resolution dynamics. The carboxamide is marked with colored bars on the 2D structure, indicating relatively high calculated rotational energy barriers, consistent with the NMR analysis using NOEs and chemical shifts, and that's consistent with pre-organization as shown. The top right panel showcases the practical tools we're using for this NAMPHIS-based analysis. We start with a curated conformer set in CCG's-Mo and generate a Gaussian output file for QM calculations. When finished, the results are imported from Gaussian into Mo's spectral analysis tool. And the spectral analysis tool GUI quickly compares experimental to calculated data. It presents least squares fits, and here's a tab for conformer distributions. And we've got interactive analyses and visualizations. In the bottom right are examples of 1D NMR signatures of piperazine CH2s under different charge states in DMSO. And communicating 1D signatures to chemists can help to quickly contextualize spectral interpretations in line with our primary goal to support drug design teams where timing is critical. This series of IRAK4 inhibitors highlights a relationship between free ligand NMR solution conformations and drug properties to guide designs for permeability. So on the left, the NH hydrogen bond donor is circled on the 2D structure. This is compound 4 from the referenced discovery and optimization paper. The color bars are on bonds with pre-organization potential based on calculations, and the table captures conformational property relationships. Intramolecular hydrogen bonds were measured by the NMR-derived hydrogen bond acidity, or ANMR, referenced below. Exposed polar surface area, EPSA, was measured chromatographically. And these top 3 show passive permeability measured by CACO2 assays. And these align with EPSA values below a threshold value of around 120 angstrom squared. The strong intramolecular hydrogen bond of compound 4, it masks the exposed polarity of the NH hydrogen bond donor with good passive permeability. Looking at the log D for both higher and lower log D compounds, where there's weaker hydrogen bonds, we still see good passive permeability, albeit weaker. And for this last row, the loss of the intramolecular hydrogen bond significantly increased the exposed polarity and showed poor passive permeability, despite the same log D as its matched molecular pair. So this is the last of the 3 unpublished highlights, AZD9833. Here we're showing the free ligand solution conformations across solvents are showing shifting of bioactive populations. So the 3D bioactive conformation is shown in green with the methyl group axial highlighted and the pyrimidine nitrogen facing front. So combinatorics give 4 possibilities as shown in the table, with the axial front conformation matching the bioactive binding mode. And the bioactive binding conformation, the bioactive conformation is present across all solvents. And its population varied from 20% in acidic water to 44% in toluene. The highest and lowest populations for each conformation are bolded, and the same conformations were observed across solvents, together with a shift in the relative populations under thermodynamic equilibrium. DMSO and D2O have relatively similar major and minor conformational preferences. However, the better solubility in DMSO makes it of higher practical value for maintaining standard conditions and for our purposes of guiding drug design. So, summary and key learnings. Potent drugs preferentially adopt the bioactive conformation in solution. Intramolecular hydrogen bonds, which can be measured. Mask hydrogen bond donors, which will improve free ligand passive permeability. The bioactive conformation of potent drugs is conserved across solvents. A semi-automated free ligand conformational analysis platform, plus use of 1D conformational signatures, can help test a design hypothesis within relevant timelines, and analysis of 1D NMR data enhances understanding within a chemical series. So, most important, I'd like to thank my analytical and structural chemistry, oncology R&D colleagues, as well as our early oncology medicinal chemistry leads for the projects discussed. I thank Elizabetta Chaperon, Martin Packer, Nicola Davies, and David Longmire for their key inspirational insights and work shown. I thank Brian E. Smith, Dan Rhodes, and Kennedy Taveras for their impactful contributions in data provided. And we've got an international NMR conformational analysis team. And I thank you for your attention. So with that, I look forward to hearing from you with some questions now and continuing after Thomas's talk as part of our open discussion. Thank you, everyone.
Thank you very much, Amber. A really, really nice presentation. We have one question in the chat. Charles, please feel free to ask yourself.
Yes, so Amber, hi, thanks
Hi.
for the nice talk. So I just wanted to confirm that the 3D bioactive conformation that you have used and some of these comparisons, did it come from X-ray crystal structure of the protein, which with the ligand shown, I guess?
Yes, that's a great point. So in all the examples I've shown, the bound conformation is taken from a bound ligand X-ray crystallography in the protein. In our 2019 JMed Chem paper, we do talk about you can work with a hypothesis that your most potent compound is already adopting the bioactive conformation. It's part of optimization so that you're reducing the energy penalty that you would pay for rearrangement on binding. You're also reducing the strain when it's bound if it's already pre-organizing. And then there's an entropy penalty if you have a lot of free motion, a lot of different conformers in competition for the binding. So we do use the crystal structure. However, in practice, you're not limited to the crystal structure if you've got really good binding affinity, which opens this up for practical uses.
Thank you.
And you can always revise your hypothesis, right? Where it looks good, this is our bioactive structure, and if you get more data, you go with your more data.
So I have a question actually. It was a very nice talk, and this is Prashansa. So all these bioactive conformations, are they like temperature or pH dependent or solvent dependent, or they are very like conserved in any change in the solvent or sample condition is not going to affect this bioactive conformation? Have you tested that as well?
Yeah, so what I understand from that is you're talking about population shifts.
Yes.
So our bioactive conformation we're defining as the one that's in the bound crystal structure. And then we want to know, has it pre-organized in solution? So this would differ from something that might be evolutionary, evolved, promiscuous. These are designed to be potent and specific. And so there's our working hypothesis again, that we're going to optimize our binding, our potency, and our specificity by having as much of the bioactive conformation locked into solution when we're starting. So it's a design, right?
Okay,
and
got it. Okay.
well,
Yeah,
thanks
okay,
for the
got it.
question.
Yeah,
Both
thanks.
really good questions. Appreciate both of them.
Thank
Hey, Amber.
Hey.
I have a quick question. That was a wonderful talk. Thank you so much. So in your talk, you've emphasized the importance of the thermodynamic components, mainly the binding affinity, the tight binding affinity. How important is it to also correlate that to the kinetic component? And I think you mentioned the residence time at some point.
Yeah, so one of the examples from, again, the JMed 2019 paper that I really loved going through is when you're optimizing your K on, you can see that you're optimizing your pre-organization, right? And so if you're pre-organized, you've got, I feel like I think it's a really important point that when you reduce your conformational entropy, you're pre-organized, so you're getting rid of one binding distraction. If you're binding preferentially the one that's pre-organized, then any binding strain is also minimized. That's your lowest energy conformation. And so optimizing your K on means that you're pre-organized, reducing your rearrangement penalties. And then for your K off, that's your protein ligand interactions and the complementarity. And so if you can pick up another structure-based drug design interaction between your ligand and your protein, you're gonna make your K off optimized, right? And so for your KD, you want to optimize both. You want to optimize both your K off and have the longest residence time by picking up that protein ligand complementarity. And you want to pre-organize your free ligand so that you have optimized your K on. Did that answer the question? That's a good question.
Yes, that was great. Thank you very much.
Thank you.
Thank you very much, Amber. I think we need to give our last speaker time to present. And excellent questions. Please keep going with the questions during the general discussion. So far, the conversation is really stimulating. So our next speaker is Dr. Thomas Williamson. Dr. Thomas Williamson received his PhD in medicinal chemistry from Oregon State University in 2000 under the direction of Dr. William Gerwick, and joined Merck & Company in 2011 after spending 4 years with Wyeth and 7 years with Roche. At Merck, Thomas served as a director of structural elucidation group, where he oversaw the NMR and high-end mass spectrometry technologies and their support of projects in Rahway and Kenilworth, New Jersey, Summit, New Jersey, Boston, Massachusetts, South San Francisco, California, and West Point, Pennsylvania. Thomas's work at Merck encompassed all phases of drug discovery and development, from lead identification and technology development through involvement in clinical development teams and troubleshooting of manufacturing processes. In late 2018, Thomas translated his industry experience to an academic setting at the University of North Carolina, Wilmington campus, where he was named the Yousry Syed Distinguished Professor of Chemistry and Biochemistry. Thomas's research group holds a special interest in marine natural products, drug discovery, the elucidation of the structure and stereochemistry of complex molecules by NMR, and the design of NMR pulse sequences to help achieve those goals. During his career, Thomas has published more than 140 peer-reviewed journal articles, 8 book chapters, and has been invited to present the results of his research at various venues all over the globe. And without further ado, Thomas, please take it away.
All right, thanks, Misha, and thanks to all of you for having me here today. This is pretty exciting. I always love these IVAN discussions. They're really great. I like the informal nature of these and the sharing of information. It's awesome. So sort of picking up where Donovan and Amber left off, was tell a little bit about our story and getting into this conformational or conformational characterization business, especially for macrocycles. And we started out with compound that many of you probably are familiar with. It's called rapamycin. It's a very important immunosuppressive agent used to facilitate organ transplantation. It's also been developed early in my career at Wyeth as a anti-cancer drug, and it also shows a lot of really unusual and remarkable anti-aging properties that gives it a lot of interest all over. And we picked up this project and we're working with one of our biotechnology partners, thinking about how we might make new rapamycin analogs to titer the immunosuppressive activity of this molecule so that we could use it for autoimmune disorders or to treat autoimmune disorders and other therapeutic indications. And we said, well, the first thing we want to be able to, first thing we want to do is demonstrate that we can actually, identify the conformational space of native rapamycin. So we took rapamycin and decided to go at it 2 ways. The first way is we actually just did sort of a comprehensive conformational search and identified every possible conformer that we could find, and then used traditional NMR parameters, our proton and carbon chemical shift, proton-proton coupling constants, and 3-bond proton-carbon coupling constants, along with NOEs, or in this case, ROEs, and use those parameters to fish out the what we believe to be the best fit conformation. And this seemed to work very well, and we put out a conformation that was almost 100% homologous with the bioactive binding conformation of rapamycin. And so we thought, well, this was great. So let's go about it a different way. And so we used our anisotropic NMR parameters, our RDC data, to basically do the same thing. And once again, we were able to mine these conformational space and pull out the primary conformer, which matched perfectly with the original conformer from the traditional NMR constraints and the bioactive binding conformation. So this was great. And so then we said, well, let's go and do it a different way. Let's take the rapamycin and use the NMR constraints, either the traditional NMR constraints or primarily the traditional NMR constraints, to use that to guide our conformational searching. And all this was done in 4th-gen and worked remarkably well and just beautifully. And we were able to, once again, identify the very same conformer or low energy conformational ensemble. And so this worked great. And so we thought, well, we're really, really good at this stuff. We already are experts. And so that was really great. And we were excited and we were high-fiving each other. And then we decided to dig a little deeper in. As we did, we decided to, well, let's take a look at the minor conformer. And those of you who might be familiar with rapamycin would know that rapamycin exists in 2 conformers depending on solvent and temperature, primarily solvent. And for instance, in DMSO, it's about 9-to-1 major to minor, and chloroform is about 4-to-1, and some other solvents is closer to 1-to-1. But basically, these 2 conformers can interconvert with each other. You could separate them chromatographically, but by the time you actually analyze them in an NMR tube, they basically have interconverted back to the original conformational ratio. And it was always assumed that these 2 conformations were analogous to that had been done or identified for a similar compound called FK506, and that you basically had a cis-trans rotameric relationship here for the amide on this piperacolic acid residue. And after 65,000 or so reports, we decided to look into this a little bit closer. And as we dived in, we realized that this is actually not true at all. And once we actually sort of went through a similar process as we described before, we actually found that rapamycin minor conformer actually has nothing to do with the amide rotamer. The amide rotamer is always in the trans configuration, and in fact, it's more of a sort of interconversion of the side chain, the cyclohexyl side chain. So we actually call this our sort of one-arm bandit model, where you basically either have the cyclohexyl side chain sort of flopping out around in space, sort of back behind the macrocyclic ring, or actually sort of being projected over the ring, where you can actually see some really nice NOEs in the minor conformer that don't exist in the major. So we thought this was really cool, and I don't want to sort of reveal everything here. Emily Kroll will be presenting this at SMASH, so definitely stop by and talk to her. She's going to have a poster presentation there, and I think that you'll find this is a really cool story. But I thought it was a really nice sort of illustration in that these studies can actually be quite a bit more complex than one might think at very first face value. And as you can see here, we just have the sort of ester bond that's sort of the rotatable ester bond that contributes to this minor conformer. So if you get a chance to go to SMASH, definitely talk to Emily, and she'll tell you a lot more about this. But right on the heels of this work, we saw a paper appear in the Journal of Natural Products by one of our good friend and collaborators, Nick Oberlees, down at UNC Greensboro. And basically, they had done a real sort of neat evaluation of taking bis-lactone macrocycle, which had unknown configuration, and decided to use NMR and DFT tools, chemical shift calculations, to see how far they could go in the assignment of this configuration. They also employed the DP4 plus technology from the Goodman Group in England or in the UK. And basically, using these techniques, they were able to assign the relative configuration of 2 of these stereo centers. And so we thought, well, that's pretty neat. But, let's see if we could actually do better. See if we can take this a little bit further. So picked up the phone, I talked to Nick, and of course he was really excited about, sort of jumping on this and seeing if we could sort of expand the sort of breadth of the NMR impact on this problem and see what we could do. So we came up with what we thought was a pretty straightforward plan. We'd take this compound and do a comprehensive conformational search using a whole variety of conformational search tools. Would then basically take these conformations and sort of match those to our traditional NMR parameters, our ROSI, our proton-proton couplings, and proton and carbon chemical shift. And then we'd assume that, based on this sort of higher level NMR analysis with these, additional NMR parameters, we'd be able to identify the correct relative configuration. And then we could come back with RDC measurements and do a sort of orthogonal validation to confirm that we had actually assigned it correctly. So we thought this would be pretty straightforward. The molecule didn't look too menacing, too ominous, but as we started gathering data, we realized that, wow, these macrocycles can be hard. And so basically what we found was that, once we did our DFT calculations for our C13 chemical shifts and our proton chemical shifts, and we found that they actually were conflicting. Our C13 suggested that it was conformer 1B. Our proton chemical shift calculations suggested it was conformer 1C. Our RDC analysis, our SVD fit, seemed to be kind of unstable, but it was sort of suggesting the conformer 1D. And then, of course, our biosynthetic arguments would suggest conformer 1A. So we basically had 4 different pieces of data pointing in 4 different directions. And so we were like, wow, we really have to dig into this a little bit further and see what we can do. So we went back to the drawing board, and we decided to expand our conformational search. We expanded our energy window to 10 kilocalories and gathered quite a few more possible conformations, tried to be a little bit more comprehensive in that search. And then went back and decided to take 3 key discriminating J couplings. So we couldn't just use any J couplings because some can be quite ambiguous. But what we did is we took some that were quite extreme. For instance, a 13.2 hertz proton-proton coupling. So we knew that this arrangement had to be in some sort of anti-configuration. And just use these 3 J couplings to, including one a proton-carbon, long-range proton-carbon coupling, and use these to filter our conformational search and kind of get things down to a manageable level. And in that case, we actually took a couple of different functionals and basis sets, did our energy calculations, and decided to go back and see if we could do a little bit better job now with this sort of more realistic starting set of conformers. And basically we used our standard C13 chemical shift, proton, and long-range proton-carbon couplings, and then of course our easy ROSY. And if you're not using easy ROSY as sort of your standard ROSY experiment, I would highly encourage you to check it out. This really gives nice, even, uniform correlations across the entire spectral width, and I think that if you use it one time, you'll be hooked like we were, and that'll become your default. But basically, we did all this and said, okay, now we'll validate those results with RDCs in the same way, and then hopefully we can actually assign this this configuration. And fortunately, by taking this approach, we were quite successful. We felt very confident now that we know the relative configuration of this molecule. The configuration of the first two centers matched the original report, and the third center actually matches our biosynthetic arguments. The proton chemical shift, carbon chemical shift, all pointed in this direction, as well as our scalar coupling constants. And then, of course, we went and did our RDC analysis in sort of an orthogonal way to verify the structure, and definitely the structure 1A was our best fit, our lowest Q factor. And so we're pretty excited we were able to tackle this, and at the same time we're quite surprised at how complex the seemingly simple problem turned out to be, and sort of gave us a little bit of a caution for jumping into these kinds of problems and thinking that they're going to be very straightforward. Right after that, we said, well, we're learning a lot here with rapamycin and with these bislactones, and there's been some other work done in the literature. So let's come up with like a sort of evaluation of different methodologies and try to come up with sort of a one-size-fits-all approach to using NMR constraints and conformational searching to assign the three-dimensional space of these macrocyclic molecules, in particular these sort of peptide-like molecules that we like so much. And so we sort of embarked on this new journey, and we started out with a very important compound called virginiamycin S1. It's used as a very important antibiotic in the animal health industry, and it's also used as a preservative in the ethanol industry, especially for fuel. So for most of the ethanol that goes into your gasoline, it's been treated with virginiamycin to inhibit bacterial growth. And it turns out that nobody really looked at the solution conformation of this molecule since the late 70s, and we said, well, I think we can probably do a little bit better than those stick and ball models, and we're fortunate in that we had a nice X-ray structure of a very closely related compound called streptogramin B that we could kind of compare to and use that as sort of our baseline for what we believed was probably a pretty good fit for the actual solution conformation. In this completely unreadable and busy slide here, my PhD advisor probably would be shaking in his shoes if he saw this. It's really just sort of a pictorial that shows that we actually looked at a lot of different combinations of conformational search engines, including Schrödinger's ConfGen, a couple of different derivations of ForceGen that we like so much, Schrödinger's macro model, and then of course the prime conformational search engine that was made specifically for macrocycles. And we used sort of three setups for that, one that only included about 100 low energy structures, one with about 1,000, and one with about 10,000. And what you can see here below it were all different combinations of NMR, traditional NMR isotropic coupling constants, chemical shifts, and then our anisotropic data, our RDC data combined with that. And we figured that the more NMR data we threw at these problems, then certainly the better your structural fit's going to be. And it turned out that at least in this case, that absolutely was not the case. And that's really sort of the take-home message here, is that more data is not always necessarily better. And what we're finding is that sort of our idea to find a one-size-fits-all solution to this conformational problem is really probably not realistic, not with the current technologies. And you actually really have to look at each problem as a case-by-case basis in order to really be able to be confident in how well your approach is going to work. And this just shows sort of the same sort of data instead of for all the atoms, the RMSD fit for the backbone atoms. And you can see here, ForceGen turned out to be sort of the champion and provided a really nice fit, particularly with just ROV data or ROE data and proton-proton scalar coupling constants. This is just sort of another view of that. If we take just sort of a single constraint comparison, you can see the kind of fit that we get with long-range proton-carbon coupling constants, 3-bond proton-proton coupling constants, just NOEs alone and RDCs alone. And you can see that NOE was the sort of clear champion, sort of our traditional go-to, and that was sort of confirmed here, followed by the proton-proton coupling constants, and then RDCs and followed closely by the long-range proton-carbon coupling constants. So we feel that all of these parameters have value, but one has to be quite judicious in how they actually apply these and how they actually work in a complementary manner. And then, of course, the sort of, I guess, the punchline here for, at least in this case, for the overall win was a sort of a combination of ForceGen as our conformational search engine, and then our proton-proton 3-bond proton-proton coupling constants and NOE constraints to really nail down this structure, and that was actually sort of our best. We feel that in other cases it would probably be different combinations of things, and what we really like to use most often is rather than use our anisotropic data as a sort of set of parameters for our initial conformational search, we like to use that as sort of an orthogonal search anyway. So I think that sort of the take-home message is that macrocycles are hard, and so you really need to be paying attention when you're doing this work, but certainly the accurate characterization of these models is quite possible. And just before I go, I want to bring up a couple of other really important leading references. There was a recent publication from the folks at Merck that was spearheaded by Chi Gao, really nice investigation into the minor conformer of a antibiotic known as aureobicidin, where she was actually looking at the cis-proline conformation of this, and we all got to have a little fun with this project, and really was a tremendous amount of work. And I think that anyone that's interested in looking at these macrocycles will want to take a look at this paper as sort of an instructional model on how one might approach these problems. Also, there was some really nice work that came from the Pfizer group and in collaboration with Armando Navarro Vasquez and Roberto Gil a couple of years ago, where they were actually using a combination of RDCs, J couplings, and intermolecular hydrogen bonds to characterize the conformational space of a set of cyclic peptides. So definitely want to check out these two papers if you're thinking about getting into this business, for sure. And with that, I'll just kind of wind up so we can have time for some discussion and questions, but I just want to acknowledge all the people that actually did this work. Of course, Emily Kroll, who spearheaded the rapamycin work with the folks from Biopharmics. I think AJ and Ann are both here today. Paul Hawkins from Apertor was very helpful there too. Of course, the bislactones, Ryan Cohen, he was amazing with that work and really sort of drove us to a successful conclusion of that project. And Jeff Robb spearheading the Virginia mycin work, once again with the folks from Biopharmics. Leandro Gil that was helping with our construction of our gels, and Armando Navarro Vasquez that was helping with some sort of custom stereo fitter scripts. So he also was very helpful as always. And then, of course, no work that we talk about would be possible without the contributions from Izu Liu at Pfizer and Gary Martin, and then of course the folks from my own group, Wendy Strangman, sort of co-director of UNCW Drug Discovery Group, and Ana Barrio Sosa and Remington Poulin. Also thank all our folks for funding Apertor, NSF, and the Yousry Syed Endowment. So with that, I'd be more than happy to take any questions, and thanks again for joining us here today, and hopefully we can have a nice discussion about this. Be more than happy to answer anything that you got.
Thank you very much, Thomas. Really interesting. Thank you for sharing your most recent forays into this magical world of microcycle conformation.
Yeah, there's something new every day, that's for sure.
I was very interested that at the end, for Virginia mycin, at the end, the most classical approach with ForceGen won out.
Yeah, I was too. In fact, when Jeff, sort of originally told me about these data, I sort of had to do a double take. There was this sitcom that used to be on years ago where the guy would say, say what? That's sort of what I was. We sat down and went through all this stuff, and sure enough, so I thought that was really, really interesting. And I think it would be really nice sort of extension of this project to go in and sort of drill in even further and try to understand exactly what is causing this sort of conflicting data. I mean, they have to be conflicting in some way in order for, not to be just an additive or multiplicative success. And so it'd be interesting to go back and see where things are getting crossed up that are leading to problems. We'll put that on the list.
Well, I think it's, please, everybody feel free to unmute yourself and just ask questions or join the conversation. I realized that I didn't do justice to the complexity of macrocycles during my little intro. So when I say conformation, what it really means, it's a conformational ensemble. So everything is a conformational ensemble. And when, NMR, we are equilibrium technique. So we are measuring, for the most part, not counting DNP, but with classical experiments, we are measuring ensemble average parameters, which means that averaging can really get you. So if you have one part of the molecule that is relatively rigid in solution, you can get quality constraints and you can really fold the structure. And the other part of the molecule is flexible and you get average constraints and you can't really use them as direct constraints because they just lead you nowhere.
Yeah, I think that's perfect, example or perfect a statement. If you look at just the difference between rapamycin, where the more parameters we put there, the more better and better fit we got, and then with virginiamycin, it just wasn't that case where we probably have some extreme coupling constants and stuff that were disproportionately contributing to the average value. Yeah.
So this is AJ Jane here, Biopharmics. Good to see so many faces that I know. I just wanted to emphasize again, picking up on Misha's point, that in characterizing sort of what quote unquote works and what doesn't, it gets very complicated because you have to look at the entire conformational ensemble that sort of fits the NMR data, but you also need to consider the extent to which actual ligand energetics are being adhered to. So with many of the methods that people use to explore macrocycles, you can end up with extremely high energy conformations. They might nominally satisfy your NMR constraints, but that's sort of yet another axis that you need to really consider and think about carefully, because it doesn't really matter if you're able to satisfy your NMR constraints if you've tied your molecule into a Mobius strip or a Klein bottle or something. So I just wanted to make that point, that the energetics is really important, and I don't think it's something that people pay enough attention to.
Yeah, that's a great point, AJ.
This is Alexei. Very nice talks from all three speakers. Very enjoy all of it. I have probably questions to each and every slide that you showed. So much depth and challenging I can see in front of us, and so much has been done already. That's great as well. Since the most fresh last slides from Thomas, this bicyclic ketone structure that you showed on the first step, you have a very nice RMSD already, like very low, that pick up the wrong isomer based on that. Is that because of the lack of the conformational space sampling, or is it?
Yeah, I think that was exactly what it was, Alexei, is when we did our initial conformational search, I think that we didn't have a wide enough energy window, and so we didn't actually get all the conformations that we needed. And then when we widened out that in that window, we had like an unwieldy, number of structures to actually do energy calculations on. So we had to use the coupling constants to kind of narrow it down to some manageable number.
But the RMSD itself was very low, impressively low. So if you sort of kind of warning here, so the lowest RMSD doesn't really mean that it's the right structure. That probably is the lesson from there. So
yeah, absolutely, yeah.
So trying to fit something, it could be artificially low, and then you will make a wrong decision.
Yeah.
Well,
But I think
Alexei,
that kind of connects back to what AJ was saying. You can create structures that fit everything really nice, but
Yeah.
it might be almost ready to explode with such high energy.
I guess we still play a role in using our discrimination and bringing in other parameters, what makes sense and what is clearly just a good fit.
Yeah.
right. It's for microcycles, like especially, you can really go in the wrong direction if you use some standard tools with a narrow energy window. If your conformational sampler is biased and your energy determination method, whether it's a force field or DFT is biased, it can really produce a set of conformers that would look great and may coincidentally have good RMSD, but would not represent the reality, would not represent the real ensemble.
Well, this probably some kind of a flavor here that we know about the energetics being sort of biased sometimes by artificially finding the partners which would be otherwise covered by the solvent, for instance, and such like intermolecular hydrogen bonding which don't exist in reality. But to me, it's like a red flag here that we usually rely on driving into the right decision based on our experimental observations. So you're sort of weighing in the energetics that is calculated in a certain level and experimentally observe NOE, for instance, or J couplings, and then suddenly in this picture, you can find a very low RMSD for your fitting, and perhaps by accident, and you would be so happy that the RMSD is so low. And that I'm talking about our experimental criteria to select the correct isomer, and then it happened to be sort of a wrong one, so that's a little bit scary in my kind of paradigm of making the decisions, because we usually rely on that experimental dominating procedure. We're driving the conformational search by our experimental constraints. So it seems like there is a certain way that these constraints could be wrong as well.
One thing I like about that is the way it feeds back to Donovan's Q&A by Misha about the implicit versus explicit, right? So it's not enough when the program spits out a confirmation and spits out a number. You need to go back and look at the data and make sure, well, is this a diagnostic NOE? Is that accounted for? Is this a diagnostic J coupling? Is there something here that will tell me and distinguish something that just the computer gave as a good fit versus something that aligns with all the data and everything that you know, even if it's something orthogonal, like the X-ray crystallography? Is your bioactive conformation captured in your curated set? Or have you not even given the computer a chance to catch the one that might be the most likely?
Thank you, Amber. Yeah, I was going to dive into this direction: implicit versus explicit versus a validation. So it's that's why I mentioned validation earlier. It's very important that whatever model we build, especially for molecules that are known to be tricky, like macrocycles, we know properly determining conformational space of macrocycles is very difficult for many reasons. It's always a good idea to have a subset of your experimental data used for validation. So whether you use, the classical approach, use your NOEs and coupling constants as explicit constraints, and chemical shifts and RDCs as either implicit constraints or validation sets. So you back calculate and see if you arrive to a model that is entirely self-consistent.
Yeah. But anyway, very nice talks, and I just want to give sort of preview a little bit of the SMASH conference that Thomas already mentioned, that it will be a poster session, but it will be also a nice talks, at least 2 talks about peptides at the SMASH conference, and one of them has been highlighted here by Thomas, the paper from Pfizer by Kathleen Farley that would be presented as well at SMASH. So, and I'm inviting you to go to San Diego to SMASH as well. Thank you.
Thanks, Alexei.
Hi, it's Peter Howe here from Syngenta. Are you using, for interpreting your J couplings, are you using the Karplus curve or are you using DFT to calculate them?
We're using DFT for most of our
thanks.
work, but with ForceGen, whenever we're using those as explicit parameters, we're going back to more of a Karplus type equation.
Yeah.
So basically, I guess the answer is both, depending on which direction we're going.
For well-validated models such as peptide backbone, NH alpha coupling constants, Karplus curves are very reliable because this is extremely well-studied system. But for a non-peptidic microcycle with general organic structure, I wouldn't do Karplus. I would do DFT.
Yeah, it's hard to believe we used to do NMR without DFT, right?
Or computation in general now.
Right.
It wasn't about without computers, some time ago.
Alexei, I think you're dating yourself.
Thomas, I just was curious, since this is a free discussion now, I saw in one of your constraints were the geminal HH coupling, you use it as a constraint.
Yes. So that was actually derived from our DFT calculations. Yeah, we went and did the DFT calculations on all those structures, and that's where that came from. That's a great point, because that's not a constraint that we normally think about, right?
Correct.
It's but we found that it was quite surprisingly differentiated from one set of structures to the next, and so we said, well, this is a good one because we know that coupling constant is pretty extreme.
Okay.
Yeah, that's great. I'm glad you pointed that out. I should have mentioned that during the talk because it's pretty unconventional. It was Ryan's idea. I can't take any credit.
Well, I think that this goes back to the point that Amber made, that you really want to find that one or a few characteristic NMR measurables that would be standing out one way or another. Sometimes it could be, even two bond proton carbon coupling constants. They're not commonly used for generating the hydral angles, but sometimes this would be the only coupling constant that really stands out, and everything else is kind of averaged. Nothing interesting.
Yeah, that's true. That's true. I think Roberto and Gil and Clemens Anklin, I think they had a real nice paper in Agavante not too long ago where they were actually sort of doing that.
Mm-hmm.
Yeah.
Amber, can I ask you a question about your solvent screening?
Alexei, sure.
So what do we learn from that? So this is you definitely show the distribution of the different rotapercent based on the solvent. How that drives the decision making for the medicinal chemists?
So one of the most popular questions we used to get was on doing our experiments in DMSO rather than D2O or in buffer. And so that was one of the questions we probed. And then for the different conformations, it's kind of alluding to some work we're working on now, looking at marketed drugs for publication and for looking at our hypothesis more closely, for looking at those marketed drugs in buffer versus DMSO versus chloroform. We've also had in our supplementary 2019 paper the bioactive for the AZD5991, that it was the same across solvents, having the bioactive present. So it's just a recurring question is one, probably the point I want to stress at this time.
So recurring question is a concern about that the solvent for the study was selected correctly. Is that something?
It's whether or not when you change solvents, are you just affecting your intermolecular hydrogen bonds, Or are you saying in one solvent, I have one conformation, in another solvent, I have a totally different conformation? So for example, I played around a little bit with cyclosporin, where in DMSO, there's around 10 conformations. And then there's this beautiful paper. I don't have the reference and the people to give them credit, but the title is something around with cyclosporin looking at a titration going from chloroform to methanol and seeing that that same conformation is present. That chloroform conformation, where it's like 95% one conformation, that is present in the methanol where there are multiple conformations. And just to check in chloroform and DMSO, I repeated their work, but instead of methanol and DMSO, and that 95% cyclosporin conformation in chloroform is retained in DMSO using this titration and monitoring those peaks that they don't go away. So I think the point is that it is there's an equilibrium there between multiple conformations, and you can shift the populations rather than create entirely new ones by going to new solvents, at least in potent selective drugs, maybe in naturally occurring peptides and natural products where the potency isn't as high. Perhaps there is more of a switch, or where you've got more intermolecular hydrogen bonds that you're breaking and more chances for self-associations. So the outer limits of that space and that statement, I don't think have been tapped. But in general, for our interests, that's still, we haven't disproven it yet.
Okay, thank you.
Hi, this is Purnima Khandelwal from BMS. I had a few questions for Donovan regarding the peptide structure conformation ensembles calculations. So I just wanted to understand the criteria that you use to select the 12 NOE constraints, because this is a really low number of NOE constraints for a molecule of that size. Just wanted to understand what was the reasoning behind choosing only those NOE constraints?
So we wanted to be 100% confident in the restraints, and we wanted to show that it could be done with such a small number, because if we're doing this in the discovery time scale, we don't have a week to pick out every single partial restraint that might be in there. That could be overlapped with another signal or might be attenuated by solvent suppression, you know. And so those 12 were selected because they were completely unoverlapped, and you know that we had high confidence in them, and we could pick them out very quickly with minimal assignment. And we get the correct structure just from 12. And I think that minimal conformer restraints, you know, it's sort of key. I think Thomas showed some of it, even Amber, you know, sometimes it was one restraint is enough to drive your conformer ensemble in the right direction. And so even for a medium-sized peptide like ours, you know, 12 restraints was enough to drive us in the right direction. I hope that answers your question.
Okay, and then did you observe any NOE diffusion at all in your NOE intensities for the mixing time that you carried out? I think you derived them from Rosie.
That's correct, yeah, and we do. And so everything, I'll call it a fudge factor. So we're not using hard distances. That upper limit that was on my slide has a 10% error worked in. And then AJ mentioned energetics. Even at that hard or that upper limit, that's not a hard limit. We set an energetic penalty for everything that crosses that hard limit. So if you have a nice low energy structure that just crosses that limit by a little bit, or at least that window of it, you know, the difference in energy between the low energy structure and how much it's violating a particular restraint, you still keep that. Because we do have other things, you know, diffusion, we're dealing with R to the -6 parameter. And so we never know, are we just sampling a high portion of the population getting a really strong NOE that's not really that strong. It's only sampled part of the time. And so there, this mention of energetics and the ability to have errors still get into your conformational ensemble, I think is really important to drive you in the right direction. If we just set hard limits, we'd get the wrong answers.
Sure.
Maybe that's why using 4 or 5 NMR, restraints points us in the wrong direction. With Thomas.
Yes, the reason I'm also asking is that you use 20 millimolar concentration, which is a little bit high, for biological samples. So did you see any sign of like aggregation at all? Because any peak broadening at these high concentrations, especially in your more constrained peptides?
We did not. We even titrated down a little bit to make sure that the peaks retain their character. I didn't see any evidence with these particular peptides. We'll say that we've seen plenty of peptides at 20 millimolar that do show signs of aggregation. And so it's important to be, to take that to heart. Yeah, it's absolutely a fair point.
Yes. Okay. So that's good to know. So, I mean, the reason that I was asking 12 NOE constraints is that, I don't know whether it may introduce any bias in your calculation. So for this case, you did mention that you obtained a calculated structure which matched with the with the expected structure, but in general, just choosing what NOEs to include, does that have the potential to introduce any bias using this calculation method?
I think the choice of fewer NOEs and J values, which have high confidence, is less likely to introduce bias.
Okay.
Whether it's this peptide case, or for instance, Thomas's dilactone, where only 3 restraints were used to narrow down the conformational ensemble. If you use the traditional 10 to 20 restraints per residue on my peptide and fed it into Forstgen, I think you're going to spend more time in the weeds figuring out which, is this Mobius strip the right conformer?
Yeah,
because
yeah.
we fed so many restraints into the ensemble, and that when we only have 12, you get a much bigger picture, and you can say, then you can look at other validating methods and say, well, do I see this other, Rosie? And yeah.
And I think what also works in your favor is that you have a very stable helical peptide. So your J coupling constants were low enough, they were not averaged out. So this is why I think addition of the J coupling constant derived torsion restraints with those limited number of NOEs, I think was like the crucial in terms of experimental. I just have one more question from Donovan. You mentioned HDX MS for calculation of the potential, like the NHs involved in hydrogen bonding. So did you consider using any NMR method also to derive, the same information? Because by NMR also we can obtain similar information.
Absolutely. I guess I'll leave it at we considered it, and I've done it for quite a few peptides in the pipeline. But for this particular example, we only used VT rather than HDX NMR. HDX NMR is rather manual and subject to how fast you can get things back in the NMR after you've introduced deuterium. This size exclusion chromatography, hydrogen deuterium exchange mass spec method has been shown to be nicely stable, so you don't have to rush so much to get your sample on the column and worry about if you're back exchanging before you can take any measurements. Yeah,
sure,
I can send over a few references after if you'd like to connect.
Yes, thank you. That's it. This is it for me.
Thank you, Purnima. By the way, can I ask if I understood correctly, the first question was about spin diffusion in the Rosie experiments?
I was reading Thomas' chat message. What did you say? The first question, which was the NOE diffusion. What was your question?
Right. So what was it about whether we observe any spin diffusion effects depending on the mixing time?
Yes, yes. So this is what I just wanted to find out, whether your mixing time was low enough that, or did you keep the mixing time high and then just, just use the, to maximize the NOE information in your spectrum. So I just, because that is also always a consideration for slightly larger peptides, etc. So I just wanted to find out, for your small enough, probably it should be okay, even slightly larger mixing time. But I just wanted to understand if you observed any diffusion related effects in your NOSI spectrum.
Right. So you're absolutely correct. So if for protein size molecules, spin diffusion becomes very significant consideration, you need to keep mixing times low. So these microcycles, they are all pharmaceutically sized, so they're all about 1 to 2 kilodalton, maybe if you like it, maybe even under 1 kilodalton. At this size, as long as there is no physical aggregation, we don't really worry about spin diffusion. It's not really, it's not at the level where it would affect our NOE constraints or anything like this. And that's also the reason why we use Rosie, not noisy, because that's exactly the size where NOE goes through the null. So that's why we use Rosie, and we've checked it many times internally on different programs. Up to 2 kilodalton size, as long as the molecule is a monomer, there is no difference between 100 millisecond Rosie and 200 millisecond Rosie.
Yes. So I think the molecular weight of the compounds that Donovan had it was a size where Rosie will give you the best information. But just for other kind of peptides, I just wanted to find out whether you guys observe them in any major way. Yep.
Minimally, but not of concern, as Misha said, and I think that window takes care of any spin diffusion you might be concerned about. We're not saying it's 3.2 angstroms, we're saying it's at about 3.2 angstroms or less than 3.2 angstroms.
Yeah, your constraints are wide enough that that is taken care of. And I have to mention, I really liked your presentation, where you do the NH temperature coefficients calculation using N15, using NH HSQC rather than just 1D, because in 1D they may start to overlap and then it may be difficult to find out. So with the resolution in the second dimension, I think it's just easier, and also at your concentration, the N15 HSQC is easier to record.
Absolutely. Even at lower concentrations, I'll say I don't think it's out of reach.
Oh yes.
It's not terribly expensive of an experiment. You're only going up to hours if you go to lower concentrations. It's not impossible, even though we have a low abundance of 15N.
Absolutely. Yep. Thanks.
I have a question. This is Gennady. So Donovan, you briefly mentioned something about solvent suppression, and by the way, I apologize if the chirping birds are a little loud. I have no control over that. But Donovan, you mentioned something about solvent suppression, and I noticed that in I think it was one of your slides, it might have been Amber's, but I caught one of the rosy pulse sequence names, and I noticed that there was an ES in there implying that excitation sculpting was used. And so it got me thinking, if these cross peaks are being used as, quantitative or semi-quantitative constraints in teasing out the molecular, the conformational ensembles, how important is it to take into account the excitation profiles of the solvent suppression being used? For instance, I know that excitation sculpting, that's a very popular solvent suppression technique because it completely obliterates your water signal. On the other hand, it has a very, very broad nulling profile, which also highly depends on, is the power level calibrated correctly, which shape pulse you're using. And traditionally, excitation sculpting in particular has a double spin echo period, which, might also incur additional transverse relaxation intensity losses. So all of this, at least in my head, biases some of the intensity measurements of the cross peak. So I guess my question is, how important is it to take solvent suppression techniques into account when feeding these measurements in as restraints?
I think it's very important, and you can definitely see that attenuation that you're describing in our rosy spectrum. I feel like I'm giving the same answer again, but there were a couple of things. Why only 12 Rahway? Because we were confident in those 12. They were further away from the excitation sculpting pulse. They were based on, I don't know if I'd call any of them quantitative, but they were based on a reference that was also far away from our H alpha signals. If we went back to the table, I think you'd find almost none of them are to H alphas for the rosy restraints, or they're all coming from NH to H alpha. So that attenuation is sort of shifted. And then the fudge factor, again, we're not really talking quantitative. We want to get this nice window to account for the fact that we're using solvent suppression. We're attenuating some of the signals. Yeah. Does that answer your question?
Yes, thank you.
Gennady, great question. Usually when the classical approach, if you need to get accurate quantitative information from something close to water, you do it in D2O. So we do all NH based measurements in H2O with water suppression, and then if you need to measure accurately something from H alphas, then you transfer the sample to D2O, same solvent composition but D2O based, and repeat Rahway experiments to get accurate information from H alphas.
Got it. Thanks, Misha.
I think that if we use flip back kind of water suppression, that may reduce quite a bit of the exchange with water, at least in our experience, as compared to presat and excitation sculpting. So just to mention that.
Thank you, Purnima. It's discussion evolved into water suppression, which is probably a good topic for another I1 workshop. But yeah, I agree with you. Flip back is very useful because it preserves water magnetization in plus Z. But if you do it with Watergate with flip back pulse, Watergate comes with a price. It has very broad spectral area that it bleaches out.
This is Krish. I am just actually having a target for that water suppression workshop. We will reach out to someone. That's a good topic in the future.
Thanks, Krish. Yeah, water suppression is always an interesting conversation.
Mm-hmm.
May take more than 2 hours.
Thinking about one comment that we haven't touched on, and I didn't put in the slide deck, but just in terms of approaching molecular conformational analysis, probably one of the first things we look at are the dynamics. So it's getting back around to Thomas's presentation as well with what's mobile, what's being averaged, and what's pre-organized. So before just diving into taking out NOEs and plugging them in, take a step back and see if you can look from your NMR whether things are flexible or if you have pre-organization. Are those CH2s diastereotopic? Is it because of chirality, or is it because of motion? And so if I were to make a flow chart, number one, do I have nice, sharp, resolved signals? Number two, can I say which bonds have flexibility and which bonds have pre-organization? And I would use the constraints, expecting to distinguish between different pre-organized structures. Maybe that will generate more questions as well.
I completely agree with what you just said, but I hope that will generate additional conversation.
So I have one question. This is Purnima again. I have one question for Amber that I really enjoyed your presentation. It was very nicely presented. And so how do you decide, let's say if, so generally for physiologically relevant conformations, you know, for these kind of biological molecules, you want to be as low organic percentage as possible. So you had chosen 1:1 aqueous organic mix. So I just wanted to understand, is there any concern with, you know, the conformation that you obtain in that particular mix of solvent, whether it is really indeed physiologically relevant, or would you like to work with the minimum organic possible that does give you the needed solubility?
Not sure that one's for me, maybe for Donovan, looking at the percentages and the mixtures. We just throw it in DMSO and we're looking for, you know, our question that we're asking is, have we pre-organized this into the bioactive conformation? And so changing the questions also influences what you're going to find for your answers. We're really focused on speed and pre-organization to optimize potency. So for DMSO, we're not going to be using solvent suppression. And we usually have a bioactive conformation either from X-ray or from looking at the potency. And we'd like to know, have we succeeded so there's like a spectrum, right? So if you're super flexible, you're probably somewhere in the middle of your optimization for binding potency. And if you're pre-organized and very rigid, but the wrong conformation, you're probably worse off for your binding potency. But if you've rigidified and locked in and captured that bioactive conformation of the free ligand in solution, that's going to be as good as you can get, I think, for optimizing your binding. You might still pick up some interactions with complementarity for your residence time. And that's really good to know in a pharma setting, because at what point do you say, okay, we've optimized potency, let's start looking at those phys-chem properties, right? There's other things we need to optimize. So maybe you want to ask somebody else about the relevant ratios for physiological, because it's a different question, I think. No one's jumping in. It was a good question.
Well, for small molecules, I guess I'll jump in. I guess for small molecules, it's chicken and the egg, because in solution, in biorelevant conditions in solution, you're in aqueous environment, probably in a buffer with some counter ions around. But when it's bound to a protein, then you can say that it's, you know, closer to a low polarity environment. So you can definitely look at it with both angles, and I think your angle is a lot more practical. You're just looking for whether the right, first of all, whether it's flexible or conformationally locked, and if it is, then whether you lock the right conformation or the wrong conformation. So this is a much more, it's a different way to look at it. And of course, when you say that there is a lock conformation, then it kind of doesn't matter whether it's DMSO and water anymore. It will, in all likelihood, is going to stay in that conformation or largely in that conformation. For peptides, for relatively short macrocyclic peptides, there was actually a seminal paper in PNAS in 2014, and they've done fantastic work by NMR showing that acetonitrile water mixtures are a fairly universal solvent, and up to 90% acetonitrile, these mixtures behave very much like aqueous. So if you go full acetonitrile with very little water, then conformational space of these peptides, of macrocyclic peptides, changes significantly. But from 10% water on to 100% water, general conformational space, and they were judging it by temperature coefficients of the NHs and some extra work, actual structural work. They say they found that there is very little difference. So conformational space is generally aqueous-like, up to down to 10% water in acetonitrile. So, and internally, we really like acetonitrile water mixtures. It's a fairly universal system. You can attenuate it really well, and I think Donovan covered really well the optimization part.
Oh, thank you.
So I think we can continue discussion. I think Amber will have to leave in a couple of minutes. So if anybody has questions for Amber, now it's time to ask them.
I have a question for Amber. So Amber, so the central theme of your talk was, locking in the bioactive conformation, and you had mentioned that a lot of times there is some sort of reference that you're comparing to, usually based on X-ray structure. My question is, have you ever encountered a situation where the X-ray conformation was potentially not reliable, and you may have to have, you used orthogonal techniques such as some sort of, docking simulations or something of that nature?
Great question. We're getting into definitions again because we're defining that bioactive conformation. So it's actually pretty exciting when there's an X-ray structure that's different within a pharmacophore series. Like, oh, that's interesting. It can bind this other way. Should we be looking at that? I think that turns out to be more of an opportunity than a wrench in the works. And another flag would be if you have poor binding potency, and that seems to be what you've defined as your X-ray structure, maybe then you need some more orthogonal techniques to investigate more. But as our default go-to, we take the bound ligand as our bioactive by definition. Thanks.
Got it. Thank you.
And thank you, everyone. I'm heading out now to something else. I have a hard stop at 1:59. So really appreciated the opportunity. And thank you, Misha, for the invitations. And thank you, Donovan and Thomas, for sharing the time with me. Thank you, everyone. Bye-bye.
Thank you. Thank you, Amber.
Thank you.
I'll jump in here and ask if there are more questions. Misha?
Well, looks like we've covered
okay.
a lot of ground today.
Yes, I really, what a great discussion. That was one of our best, I think one of our best discussions and that we've seen, at least in my opinion. John had to leave early, and so I will express his thanks for everyone, Misha for putting this together and all the speakers, and for everyone who attended. We had a great turnout. And so if there are no more questions, I'll conclude the meeting.
Thank you very much.
Okay. Okay.
Thanks, everybody.
We have this little thing. The gavel, so I will. So everyone.
Now it's official. Well, thank you very much, everyone.